Welcome to channel Python Science and Data Science. My name is Luciana. I am PhD in Mechanical Engineer and I will help you to program in Python. Please subscribe to the channel and give it a like. I need your support. If you would need help with some kind of work in Python program, please contact me at lucianafem@gmail.com and I could give you a solution. In that first video, I am going to teach you how to create the Moody diagram using Python. I am talking about fluid mechanics here, okay? For those who don't know, the Moody diagram is a graphic that relates the Reynolds number to the relative roughness of a pipe to give the value of the friction factor. The graph is obtained by two equations, one for the laminar regime and another for the turbulent regime. The equation in the laminar regime, when the Reynolds number is less than 2300, is a super simple equation to solve. But when the regime is the transitional or turbulent, we have a nonlinear equation that is our variable, which is the friction factor, appear on the both sides of the equation. And to solve this, must use numerical methods to solve it. This equation is known as the Caulibrook Equation. With the fsolve function of Python and quicking an initial value, we will be able to find the friction factor. See the Moody diagram. It is on the logarithm scale in the abscissa and in the coordinate. So our chart will also be constructed that way. Let's start. Look at the whole script. The first thing to do is import the modules that will be used. I imported 5 modules here: the matplotlib point plot, scipy point optimize, numpy, math, and matplotlib.ticker. From scipy point optimize, I just imported the fsolve. The numpy module is a programming language that deals with multidimensional arrays and matrices. The second step is to define the initial values of the lists that will be created. I have created 5 empty lists here: F1, F2, Re1, Reg1, Re1 only now with uppercase letters, where these initial values will be used within the for structure to be created. The Moody diagram that will be created will contain 18 different relative roughness values. Values are shown here in brackets. They range from 0.00001 to 0.05. Now I will set my first for loop structure. Remember that for loop is used to repeat a specific block of code to no number of times. In the first for loop structure, the program will calculate the value of the friction factor for each relative roughness contained in the RUG array. The second for loop structure creates one array with the Reynolds number values. I put a range to create 10 values between 2300 and 10 to the power of 8, range from 10 to the power of 7. These values are only to find the value of the friction factor in the turbulent regime. See that begin in 2300. I created here an array of these Reynolds number values because I will need to know the size of this array. I told you the size is 10. And now is the time for defining Caulibrook's function, recalling that the logarithmic functions and the square root must be written by calling functions from within the library that was imported at the beginning of the program. Since the function present here is not linear, I kicked a first value that is 0.0003. Then the fsolve function is called with that first initial value. The value of the friction factor is a float number, and I used the around function to approximate the value to the third decimal place. These extend and append commands create arrays with the values of the friction factor and the Reynolds number considering the initial values defined there at the beginning. What has been done so far? Two lists were created. One with the Reynolds number and the other with the friction factor for the program to create the graph. The Reynolds number will be the abscissa and the friction factor will be the coordinate. But we have a problem here. We want the graph to be of different colors for each relative roughness value. Then we will solve this by creating a third for loop structure that separates all the lists of friction factor and the Reynolds number for each relative roughness value. For this, we have to know how many lists should be created, and this div variable will give exactly that number. The variable div divides the length of the array containing the already calculated friction factor values. I know they were 180 by the length of the range variable that is 10. The result will be 18, and thus we will have our Moody diagram containing 18 different graphics. The round command was used to transform the number 18 from float type to integer. That's all. The next for loop structure was created to make the separation from the list. We can take an I that varies from 0 to div, that is from 0 to 18. Remember, the 18 is not taken, the loop stops in number 17. We will continue to have 18 lists whose I will vary from 0 to 17. The re1 list and the f1 list variables return a whole list of 10 elements array for each relative roughness value. The f1 list underline separates the list 1 and p takes the last value of the friction factor from this list. Why did I do this? Because I am going to put on the graph the value of the relative roughness at exactly the same value as the last value of the friction factor. To create the chart, I use this plt.plot command by taking the re1 list and f1 lists for each value of I. With the command plt.title, the graphic title is placed. To write the value of the relative roughness and its position on the graph, I used the plt.annotate command. plt.xlabel and plt.ylabel are commands to name the axes. plt.xscale and plt.yscale place the x and y axes and on the logarithmic scale. PLT point text is just a text to write relative roughness on the right side of the chart. The PLT point AXV span command fill in gray on the chart the transitional zone from the Reynolds number between 2300 and 4000. The PLT grad command was called twice to represent the axis grids. Grids in the full values will be different from the grids of the intermediate values. Commands such as ax.yx.set underline major or minor underline formatter write the values of the x in x and y. The whole of the transitional regime and the turbulent regime have already been created. So, what is missing now? It lacks to create the part for the laminar regime, which is the easiest. So let's do another for loop structure. We'll begin with the initial value of the leashes that will be created for the number of Reynolds and the factor of friction that will be created. Empty values like you can see. Our for structure here will be for the Reynolds number from 700 to 2300, incremented by 50. This calculates the friction factor for the laminar regime and creates a list to insert each of these values. Another list is also created to place the corresponding Reynolds numbers. Note that is the laminar regime, it doesn't depend on the relative roughness and, therefore, it is not necessary to put in the graph the relative roughness. Let's put our program to run and see our Moody diagram is done. Then the Moody diagram was created. Don't forget to subscribe and hit the notification bell for more updates. I'll see you in the next video. Thanks so much. Bye.